This meeting is being recorded.
All right. Hello, everyone. Welcome back to Hottest for spring 2026. So for our first talk this term, we have Benedikt Ahrens, who will present a type theory for comprehension categories. So take it away.
Thank you very much. Thanks for having me. I would like to introduce the people, first of all, that I've worked with or collaborated with on this work. So this is Nyusha, Niels, and Paige. Particular credit for this work goes to Nyusha, who started this work as a master student under my supervision, and then Nyusha is now doing a PhD with Ambroise Lafont and has been able to continue this work during the PhD. And so most credit goes to them for this work. And also the slides, I adapted slightly from Nyusha's slides that they prepared for another talk. So all the errors are mine, but everything that is good about the slides is, of course, Nyusha's. What's the setting for this talk? In this talk, the starting point for this talk is Martin-Löf type theory, which, as we all know, I think in this community, can serve as a foundation for proof assistance and programming languages. And when we think about semantics for Martin-Löf type theory, then there are several categorical notions like contextual categories, categories with families, display map categories, and so on, that have been used to give semantics to Martin-Löf type theory. Among these established notions, maybe the notion of comprehension category is important, as it subsumes the other notions in a very specific sense. In a different work with Peter Lampstein and Paige North, we have kind of identified these other the two categories spanned by these other notions, contextual categories and so on, as sub-two categories of the two category of comprehension categories. So comprehension categories can be seen as a framework in which to analyze, study, compare these other notions of these categorical notions that have been used for the semantics of type theory. So comprehension categories in themselves seem to be interesting objects. When we interpret Martin-Löf type theory in comprehension categories, so this is a picture of a comprehension category. I will explain this much more mathematically precisely in detail. I will give a detailed definition. What is important now is that when we interpret Martin-Löf type theory, when we give semantics of Martin-Löf type theory in a comprehension category, then we do not actually use all the features of a comprehension category. What precisely we are not using, I will explain. But for now, very superficially speaking, there are two options. We could restrict the comprehension categories, or we could focus our attention on particularly simple ones that where these features that we are not using are kind of trivial in the mathematically sense, if these are fully faithful or discrete comprehension categories. I will come back to that. Or what we are interested in this work is we can actually change the type theory. We can change type. We can go away from Martin-Löf type theory and develop a new type theory that is more expressive, that does allow us to talk about all the features of a comprehension category. And that's what we are doing. We are developing, we have developed a type theory that we call CCTT, for comprehension category type theory. Not a very good name, maybe. And so this is a more expressive type theory, say, that is kind of custom made to be interpreted in comprehension categories. That's what the talk is about. So why do we not want to restrict the models? I hope to convince you that we would actually miss some interesting examples, first of all, of comprehension categories. If we restrict to these particular, if we do not look at these interesting, at these sort of maximally general comprehension categories, and we would also miss out on some features that we might be interested in the type theory. I will explain this in more detail now after giving some precise definitions. Okay, this is the outline for the talk. I will review the definition of a comprehension category, and I will go back to the motivation, and then in these three parts here, I will talk about some, what we have done, namely developing a type theory or the rules of a type theory, CCTT, and then talk about how the feature of subtyping that is captured by CCTT, and I will talk about type formers for CCTT. Okay, so what is a comprehension category? It consists of, first of all, a category C, down here. Then we have a cloven fibration. In our case, we always assume all our fibrations to be cloven. P, so we have a category T here, a functor P that is assumed to be a cloven fibration. And we have a comprehension functor from T into C arrow that is supposed to preserve Cartesian arrows. And we want this diagram to commute here, this triangle. How should we think of such a comprehension category? No, sorry. I should first mention that a comprehension category is full if this functor chi is fully faithful. This will be important later on. And it's split if P is a split fibration. Now let's think about how we should think about a comprehension category. How does a comprehension category model Martin-Löf type theory? Well, the category C down here, it models contexts. And then this category T here, say the fiber of P over an object, a context gamma here, we think of as the types in context gamma. The re-indexing that is given by, or that is part of the cloven fibration P, models substitution. So if we have a morphism down here, a morphism of contexts, in quotes, then we can pull back or re-index a type over the target context to obtain a type over the source context of that substitution. The comprehension here, gamma, models context extension. So if we have the objects in T, we can think of as pairs consisting of a gamma of an object in C, a context gamma, and a type here called A living in that context. And we send the pair gamma comma A to the extended context gamma dot A and a context morphism, or a context morphism gamma A from the extended context gamma dot A down to gamma. And then kind of indirectly, we model terms. So if T is a term of type A in context gamma, then such a term is modeled as a section of gamma dot A, a section, in the category C. Okay. We have used almost all the features of a comprehension category, but we have not talked in this interpretation about morphisms in a fiber, in the fiber T gamma. That is, we have not talked about, or we have not used morphisms in T. For instance, morphisms that both between two morphisms over the identity on a context gamma. Yeah. And Now let me go back to our motivation. So when we interpret Martin-Löf type theory in such a comprehension category, we do not make use of the morphisms in T. And this is why very often the morphisms in T are taken to be trivial. That means that T is assumed to be discrete. Or the morphisms in T are assumed to be kind of coming from the category C, meaning that this functor chi is fully faithful. So morphisms in T are trivial in some sense, are not of interest. But in principle, a comprehension category can express both morphisms between contexts. That's what we are using to interpret terms, Martin-Löf terms, and morphisms between types. And that's the kind of the starting point for our work. Now, you might ask, other interesting examples of comprehension categories with non-trivial type morphisms. Otherwise, this is all not a useful consideration. But yes, there are interesting examples, notably examples arising from algebraic weak factorization systems. So intensional type theories are often given semantics in an algebraic weak factorization system. There's a paper by Gambino and Larea about only about models in algebraic weak factorization systems. And algebraic weak factorization systems give rise to typically non-full comprehension categories. So I will not give the definition of an algebraic weak factorization system, but it involves in particular a monad, say R, on the arrow category of C. And then we can build a comprehension category where the category of types is given by the Eilenberg-Moore category of R. And we have a forgetful functor here into the arrow category of C. And that functor is usually not full. It is, however, usually faithful. And we are interested in capturing this extra semantic structure that, for instance, comes from algebraic weak factorization systems in our type theory CCTT. So what are some such examples of non-full comprehension categories? We can build a category of a comprehension category of groupoids that arises from an algebraic weak factorization system where the category of types consists of split vibrations and morphisms of split vibrations that preserve the vibration structure, the Cartesian lifts on the nose. And then we have a forgetful functor down to the arrow category on groupoids. It's not important here that we work with groupoids. The same works with categories. It's essentially the same example, groupoids and categories. We can look at other non-full comprehension categories. If we take a topos E, then we can build the following comprehension category. The category of types is the slice category, so of E over the subobject classifier omega, and then the comprehension functor maps a morphism into omega into the subobject classified by that morphism, and that is also typically not a full functor. So this comprehension category is not full, and this is an example in a very similar style. If H is a Heiting algebra, then we can build this comprehension category again with the comprehension chi being the functor that maps a morphism into H into the subobject classified by that morphism. Okay. So I hope I have convinced you that there is a reason for looking at not necessarily full comprehension categories. And in this work, we design rules of a type theory that reflect the structure of not necessarily full or discrete comprehension categories, and we call that CCTT. We show how some of the rules of CCTT can be seen as rules for coercive subtyping. This is extending work by Coraglia and Emmenegger. And we also give rules on top of CCTT for sigma, pi, and identity types, and rules that make these type formers compatible in some sense with subtyping. I should point out that the whole work is based, or this talk is based on a paper that we have recently published called From Semantics to Syntax, a type theory for comprehension categories, that you might find on the archive. Okay. This is the motivation for the work. I will now go a little bit into the technical details of the work and explain a little bit what CCTT looks like, what choices there are to be made, and also how to make it simpler. It's pretty complicated, but one could think about simpler variants. So these are the judgments of CCTT. We have 6 kinds of judgments. We have the first judgment that is that something is a context. So gamma is a context. Then we have morphisms of contexts. So here S is a context morphism from gamma to delta. So the judgments 1 and 2 together kind of, and 3, of course. 3 is a judgment for equality of morphisms of contexts. So the first 3 judgments are essentially describing the category C, the base category C. Then we have a judgment number 4 says that A is a type in context gamma. Judgment number 5, and this is an interesting judgment, says now that T is a morphism from A to B in context gamma. So it's a morphism in the fiber over gamma. And then judgment number 6 is gives us an equality judgment for morphisms in the fiber. So the important judgments, maybe the ones to focus on, are the judgments 5 and, well, it's the judgment 5 and 6 and the corresponding equality judgment. And to compare this with the usual judgments of Martin-Löf type theory, there we only have, well, we have the judgment that T is a term in context gamma, and we have an equality judgment for terms in context gamma. So these are the original judgments, and these are the judgments for terms of Martin-Löf type theory, and these are judgments for type morphisms in CCTT. Maybe I should mention here that this judgment for explicit substitution, that's also one that is not a judgment of Martin-Löf type theory, but there are other works that have considered such a judgment, in particular work by Coercive, Garner, and Hoffman a few years back. They have also considered this such a judgment of explicit substitutions. And we are adopting this because we really want our type theory to be a reflection of semantic features, of the features of a comprehension category.
Okay. Is it significant that you haven't included a type equality judgment here?
it is significant in the sense that we do not want it, because we want to reason up to isomorphism of types, not up to equality of types. In the paper that I've just advertised, we also consider a split variant where we discuss substitution, not or preservation of structure, not up to isomorphism of types, but up to equality of types. And then things become, well, some things become much simpler, of course, but sort of that is a variant of CCTT that one could implement if one was interested in something more practical, maybe, and more usable. And I should also mention, I mean, I will come back to this later, but there's also kind of parallel work by a group of French researchers that approached everything from like that, who also design type theory. They approach everything more from a syntactic point of view, and they zoomed right into a type theory with that is split, that has an equality judgment. Yeah. So that's a choice to be made that we do not want to make from the start, but that is would be very reasonable to integrate. Okay, so judgment 5 is kind of stands for morphisms as before in this picture. The judgment 5 stands for morphisms, say T, in between two types in the same context, from a type A to a type B, say, that lives over the identity morphism on a context gamma. Once one has this set up, one can introduce a term judgment. For instance, as we hear, gamma, in context gamma, A is a term of type capital A. That could be a macro for saying that A is actually a context morphism, a section of the canonical projection from gamma.A down to gamma. Yeah. So there's no primitive term judgment, but one could have such an abbreviation, like a macro judgment. And this is, I think, in a few places in the slides, I will use this macro. So when I talk about terms, what I really do is I talk about context morphisms. Okay, so what does this type theory CCTT, or actually what do the rules? I should say we don't define one type theory. We have not decided on base type. So what we do is we're also not thinking about an initial object in some category. We just study the rules or propose rules for this for a type theory, and we call this collection of rules. We call that CCTT. What do some of these rules look like? Well, here we have rules kind of that express that contexts form a category. So if gamma is a context, then we have a context morphism that we call 1 from gamma to gamma. If we have two composable context morphisms, S and S prime, where S goes from gamma to delta and S prime goes from delta to theta, then we can compose them. So S prime after S is a context morphism from gamma to theta. We can express, or we do express, equalities between context if we compose a between context morphisms. If we compose a context morphism with the 1 on the left and the right, we get the same context morphism, and so on. This here is associativity of composition. We have similar rules for the category of types. I will not go through these rules. It's pretty obvious.
Could you say, I guess maybe it's not quite obvious enough to me, what judgments are those? The rules for the category of types? Like what do those look like, or which judgment are they expressed in terms of?
Well, we have, we are using these judgments 4, 5, and 6. And we express that every that we can, well, what do we want to express?
Oh, I see. Okay. Okay. Yeah. 5
morphisms. We can compose fiber-wise. We can compose morphisms between types within each fiber, and we have an identity morphism on the type A. So everything is expressed fiber-wise.
Yes. Okay. So yeah, 5 is the type morphism judgment. So that's, yeah, use 5 and 6. Right.
Yes.
Thanks.
Exactly. So these are the objects and these are the morphisms, just like these are the objects and these are the morphisms. Yeah, thanks for asking. Okay, yeah, so the rules look similar. They're just fiber-wise. An obvious theorem that one would like to prove is a soundness theorem. Every comprehension category models the rules of CCTT. And this is extremely straightforward, and it's designed to be extremely straightforward, of course. Okay. Now, this is what we did with Nyusha in Nyusha's master thesis, and then we learned a bit later that of this paper by Coraglia and Emmenegger, that studying non-full comprehension categories syntactically can be viewed as some sort of subtyping. And this is what I want to explain now. So Coraglia and Emmenegger observed that these vertical morphisms, so morphisms between types in a given fiber over, say, gamma, they can be thought of as witnesses for coercive subtyping. So we could, this judgment, where T is a morphism of types from A to B in fiber gamma, we can think of it as saying that T is a witness that A is a subtype of B, well, by way of T, in the fiber over gamma, in context gamma. If we think about it in this way, then what we want to have, of course, let me start with this rule. What we want to have is that any so if A is a subtype of B, and we have a term of type A, then we would like to construct a term of type B, of course. So a term of type A we should be able to coerce it to a term of type B. So and this intuition is kind of made precise in this rule that we can derive, that is sometimes called subsumption, but it's weird because it's weird to call it subsumption because we are explicitly not doing subsumptive subtyping, but coercive subtyping. But I think logicians know this rule is subsumption. So what does this rule say is that if A is a subtype of type B in context gamma, and A is a term of type A, and recall that this is a macro for saying that A, the small a, is a context morphism in the section of the projection from gamma dot A to gamma, then we can build a term of type B, and the term is the following. What we do is so T is a is a type morphism, but if we apply the comprehension, so T lives sort of in the category capital T on the left-hand side of our comprehension category. Gamma dot T is the comprehension of the morphism T, and that is a morphism of contexts, and we can compose the morphism of contexts A with the morphism of contexts gamma dot T to obtain a morphism of contexts which we call B here, that goes from gamma to gamma dot B. So this composition here, that is a term of type B in context gamma. Yeah. So if we have a type morphism, aka a coercion, if we want, then its comprehension acts like a function that allows us to produce a term of type B from a term of type A. Okay. We also can check that our intuition works correctly with the subtyping intuition in mind. Of course, we would like to have weakening for subtyping, meaning that if A is a subtype of A prime, modulo A or via a coercion T, then if we substitute in A and in A prime, modulo some, or if we weaken in particular, then the weakened A should also be a subtype of the weakened A prime, modulo or via a coercion that here is obtained simply as substituting in T. Yeah. So this is a technical lemma that just says, okay, we also have weakening. The weakening that we have is compatible with the subtyping idea. And this rule, we derive it in particular using the substitution rule that we postulate. Okay. This was the review of like just basic CCTT and its intuition, the intuition of subtyping that it generates, or that it permits. In the last part, I would like to talk a little bit about typeformers and how to add typeformers to CCTT. Why is that? What do we have to do here? Well, typeformers, of course, they make new types from old types. Typeformers also come usually with term formers. We call them typeformers, but actually we should say type and term formers. So typeformers usually produce terms also, or they come with term formers. So here we also build some context morphisms. But also, since we have non-trivial morphisms of types, the typeformers should also act on morphisms of types. So there should be some functoriality happening. You know? And the whole task now is to explain how typeformers extend to morphisms of types in a way that makes them compatible with also the term formers. So what we want to do specifically is we want to extend, say, CCTT with a typeformer like sigma types, and we want to do this both in the syntax but also in the semantics, meaning that we want to also identify structure on a comprehension category that is suitable for interpreting the rules for sigma types. And we want to do this in a way that is compatible with the subtyping point of view, meaning that we want to do this in a way that is a good functorial action for these typeformers on type morphisms, not just on the types themselves. I will go through the example of sigma types. I think sigma types are the simplest typeformers. In the paper, you can also see it for pi and identity types. In particular, the identity types get very, very complicated. So it's not very good to do before dinner, maybe. Here are some rules, some of which will look familiar to you and some of which will look a bit maybe not so familiar. The first rule here to extend CCTT with sigma types is the sigma formation rule, and that is a standard rule. If A is a type in context gamma and B is a type family, say over A, or is a type in the extended context gamma.A, and we can produce a new type sigma AB in context gamma. The introduction and the elimination rule, they are phrased in terms of context morphisms. So if we have again a type family B over A, say, then we have a context morphism pair sigma AB that is a morphism from gamma.A.B to gamma.sigma AB. That's the introduction rule. And as an elimination rule, we have a context morphism from gamma extended by sigma AB to gamma.A.B that we call projection. So this is phrased in terms of building pairs and taking apart a pair. We want that intro and elim are introduction and elimination rule are inverse to each other in both directions. So these are sort of strong sigma types. So we postulate that both compositions, projection after pairing and pairing after projection, are their respective identities. But also, so these rules are kind of standard, maybe. The last rule is a rule that now talks about morphisms of types. We can, on the end, it's about the commutation of substitution with the type formers. So we state here that if we look at the type sigma AB and we substitute in the type sigma AB, then that's the same as first substituting in A and B separately and then building the sigma type. So this is a usual condition. We use a macro here. It's this turnstile with the tilde. That is a macro for several judgments where we postulate morphisms, type morphisms in both directions, and we postulate that their composition, their respective compositions are the identity in either direction. Okay. Now, as a final part for these rules, what we want to have is we want to have that subtyping as the subtyping judgment kind of lifts to the type formers. So what do I mean by that? If we have a morphism, a type morphism F from A to A prime, and a type morphism G from B to B prime, and this is not well typed, hence it cannot go from B to B prime, but it needs to go from B to B prime, like adjusted, modulo some re-indexing. So if we have such a pair of subtypings, we want them to produce a subtyping of the sigma types. So we want a coercion from sigma AB to sigma A prime B prime, which we want to call sigma FG. So this is about, in other words, it's about functoriality of sigma. Sigma, of course, should act covariantly in both arguments, A and B. And what is important is that this type morphism that we want to produce here, it should be compatible with projection and pairing, and it should be, in particular, when we view a type morphism as a context morphism, then this should be there should be a commutation happening. So we can, when we have f and g, we can view f and g when we apply the comprehension. Sorry, when we apply the comprehension to f and g, we get context morphisms, which we have here and here. And what we want is that when we apply the comprehension to sigma fg, then it relates in a specific sense to the comprehension of G and the comprehension of F. And we can make this link precise using the projection and the pairing to mediate between them. And then once we have established, once we have such a functorial action, of course we want to express also that it is functorial, meaning that it maps, if we have an identity here and an identity here, that sigma of the identity and the identity again is mapped to the identity, and the same for composition. And this is all, it requires some compatibility isomorphisms left and right, because otherwise it will not type check. So it's pretty difficult to write down precisely, but the idea is very simple. We want to define a functorial action on the type formers, for the type formers, such that the action in T matches up with so on the level of type morphisms, matches up with the action or with the term formers in the world of C, of the base category. So type morphisms and context morphisms should go hand in hand. Okay, so the rules, I have not written down the rules. They are very complicated. They're in the paper, but they're expressed to make precise this intuition or these ideas. And finally, we want to define also semantic structure on comprehension categories that allows us then to interpret the syntactic rules in such a structure. And so we define for a comprehension category to have subtyping for sigma types. We want the comprehension category to have dependent sums. We want to have for any morphism F and G like this in a fiber of T. We want a morphism sigma Fg from sigma AB to sigma A prime B prime, such that the comprehension of this type morphism is exactly this composite that I've written down here, and such that sigma preserves identities and composition. So again, the semantic structure gives rise to the syntactic structure, and they are developed kind of hand in hand. And in the end, this theorem is by design, the proof is trivial. Any comprehension category with subtyping for sigma types models CCTT extended with subtyping for sigma types. As a sanity check, it's of course useful to understand what these sigma structures are when the comprehension category is fully faithful. And we can then say that our sigma structures are equivalent to those studied by Lumsden and Warren. There's also a sigma structure, or Jakob, he studies sigma types in his book, and Jakob's sigma structures give rise to ours. We have not been able to derive the opposite direction. That also points to there seems to be maybe a gap in the literature comparing different formulations of logical structure. So if anybody knows about such literature, I would be very happy to hear about it, because that is it's a difficult and cumbersome undertaking to compare different type formers semantically and study their relation. Okay. So I will not go through the other type formers, but it looks in principle similar, but it gets a bit more complicated, in particular, as I said, with the identity type. The full details are in the paper, in the archive version of the paper. In the end, I would like to mention some related work, because there is quite some interested related work. Firstly, there's a paper by Méliès and Seilberger, or actually I think several papers. They study, give a categorical semantics, a vibrational view of subsumptive subtyping. So the difference between subsumptive subtyping and coercive subtyping, for those, at least as to the extent that I understand it, is that in subsumptive subtyping, you don't have a trace. Subtyping happens without a trace. Whereas in coercive subtyping, there is a function that mediates between the subtype and the supertype. And in particular, there could be several coercion functions between two same types. In subsumptive subtyping, that does not seem to be possible, as far as I understand it. I have mentioned a paper by Coraglia and Emmenegger, where they study generalized categories with families, which are equivalent to non-full comprehension categories. They study type morphisms as witnesses for coercive subtyping. So the idea of looking at these, at interpreting these type morphisms via subtyping, I think that is from Coraglia and Emmenegger's paper. And in that paper, they also specify some of the rules for sigma and pi. They do not discuss identity types, though. So, sloppily said, one can say that what we are doing, we are kind of completing Coraglia and Emmenegger's work and looking at it in more detail and figuring out some of the technicalities. I think that summarizes the relationship reasonably well. Then there are two other works that I want to mention. I've mentioned this research group of French people, Laurent, Lennon, Bertrand, and Maillard. In a first paper, they develop three different type theories. They are interested in having definitionally functorial type formers. So they develop, they extend Martin-Löf type theory. In particular, one of these type theories that they call MLTT COE for coercive. So this is a type theory with coercive subtyping that looks a bit similar to ours, to our type theory. One difference is that they allow at most one coercion between any two types. So they don't keep track, so that there cannot be a choice of coercion function. And substitution is strictly functorial. So their type theory looks a little bit similar to the variant CCTT split that we also explain in our paper with a strict substitution. I don't think they have explicit substitution in their type theory, though. And then in a follow-up to the previous work, in a very recent paper that was also published in POPL, they develop a type theory that they called ADAPT-TT, which is modeled by split generalized categories with families. So split generalized categories with families are equivalently split, not necessarily full comprehension categories. So this type theory, again, is similar to our type theory, but it's again split. And they have a general framework and another type theory or like a framework, ADAPT-TT2, where they define type form, or whether it allows one to define type formers that are automatically functorial. This is just some of the related work that there's a more extensive discussion of related work in the paper, but I felt like these are the ones that are maybe worth mentioning in this particular talk. Okay, I come to a conclusion. As a summary, we have developed CCTT, which reflects the structure of a comprehension category, and in CCTT, as compared to, say, Martin-Löf type theory, we kind of gain back the extra dimension of type morphisms, which can capture a phenomenon that is coercive subtyping. In the future, we would like to explore how these type morphisms can be used in practice. And for this, we can again look at specific models of, say, MLTT in algebraic weak factorization systems. And when we look at these, for instance, in the model given by groupoids or categories, there the type morphisms are morphisms preserving the transport of structure along identities strictly, not just up to isomorphism, not just in a categorical way, but really up to definitional equality. And then inspired by what happens in certain models, one could reflect this back into the language, and one could hence add rules to CCTT that express this strict preservation. That would sometimes be helpful, I think, in practice. In particular, we have found one commonly used function that we use all the time in MLTT, or in HOT, that is a type morphism in these models that would be the first projection of a sigma type. And so one could add a rule to, say, CCTT that expresses that the first projection of a sigma type commutes strictly with transport. But we have not looked into this very deeply, but it could be that this gives rise to hopefully a more useful type theory. That's all. Thanks a lot.
Great. Well, thank you very much. Let's all silently applaud for the speaker. And if anybody has a question, you can feel free to just unmute yourself and ask. I guess maybe I will start with one. Going back to the rules about subtyping for sigmas, I was kind of expecting that you would say that, well, yeah, exactly, that these rules are derivable from other things, because the elements of sigma types are already determined up to isomorphism. By like, I mean, I don't know what all the rules are, but I would have imagined that if you know something about the relationship between context extension and type morphisms, then it should, at least up to isomorphism, maybe 0.2 is off by the reindexing on both sides, but that at least maybe that these rules minus maybe 2 should be a weaker version, would follow directly from some structural rules of the theory. I wouldn't expect that for like identity types, for example, because those are not given by, you don't have beta and eta for those. But if you have strict beta and eta, I'm surprised that these are not automatic, at least weakly automatic.
It's a good comment. I'm not sure. I could Nyusha is here. We could ask Nyusha if they have anything to say, but to me it's not clear how to derive these rules. I would have to give it some thought. Don't think I can answer anything clever right now.
Can I say something?
Please.
Yes, so hello, I'm Nyusha. So these rules, I'm not sure if I understand what you say, but for example, this in point 1, the rule that you see here, so this is now about about the morphisms in the fiber, right?
Mm-hmm.
But then all the other rules that all involves like the beta, eta, and all the usual sigma ones, then they only talk about the morphisms in the category C, not in the T. And then chi is not fully faithful in this case. So I kind of don't understand how you want to put it back to T, the stuff and derive things in T. Like, yes. So the comprehension functor applied to this thing that there is in the conclusion of point 1, we already have it. And that is like what is in point 2, the composition in 2. But
right.
Just the thing itself, yes, maybe, yeah. Okay, that was what I wanted to say.
Okay. Right. Well, I mean, I'm definitely familiar with, well, mostly CWFs and things like that, but certainly in the case where these things are full, so I might be missing something there. But I guess what I'm thinking is just that we basically know that the elements of sigma AB are the same as the elements of gamma dot A dot B and right. Up to isomorphism. And so if there's some that somehow that and I guess, do we know something first of all about how the context extension interacts with the coercions?
Context extension. I mean,
so I guess, we have like this, for example.
We have weakening. There are a whole lot of rules. I'm not sure. I don't know all of them by heart, I'm afraid.
Right.
I think
so. There is. Can I say something? There is this. Yes.
Okay. Right.
I think the difficulty in general is that if I go to a picture of a comprehension category, is that much of what we know about, what we know about terms happens here or here. And what we need to add is stuff here that is suitably mapped onto the existing stuff here. It's not, we don't know how to go backwards unless chi is fully faithful. So maybe this is what Nyusha tried to said. In other words, we cannot map structure backwards from CRO to T, but we have to kind of postulate that stuff exists here that is mapped suitably via chi to something that we already know about.
Right. Okay. So right. So it could be that my intuition is wrong here, definitely. I guess what I was thinking is that in the case of sigma types, you do know that, like we do know something about, what morphisms between, gamma dot sigma something are. Like we know something about the morphisms between gamma dot, sigma AB and gamma dot sigma A prime B prime, because we know that those are the same as the morphisms between gamma dot A dot B and gamma dot A prime dot B prime, right? So therefore I was thinking like somehow then shouldn't I be able to parlay that into knowledge about what the morphisms between sigma AB and sigma A prime B prime are. That's my reasoning.
Yeah, I have to think about it more, I think.
Yeah. Okay, well, anyway, that was a helpful discussion. Thank you. Any other question?
I'll ask a question. So thanks for a nice talk. Do you have any thoughts about how universes would work, and is there a different kind of univalence one would have, and so on?
Oh, that's a great question. No, I have not thought about this at all. So to express universes, I guess you're asking because the univalence axiom states that so there we refer to terms of the universe type, and the identity between terms of the universe type should be the same as the isomorphisms or the equivalences between the types. So there one could possibly think about whether one could phrase it, the univalence axiom, maybe differently, not with respect to terms, but with respect to type morphisms of some sort. Is that what you have in mind?
Yeah, I'm just wondering whether we use the T or the arrow category of C when we're trying to formulate it.
It's a great question. I don't know the answer, and I have no intuition for what happens when, what the other univalence axiom would look like, one expressed with type morphisms instead of terms. That's an interesting question that I will discuss with my co-authors later, right away.
All right, great, thanks.
I have a question as well. Hi, Benedikt, it's Jacopo.
Hi.
Well, thanks for the great talk, and well, for doing this work as well. So first of all, I have a comment actually, because the idea of using the vertical arrows in a fibration to model subtyping actually was coming from another guy here in Genova that you've met last year, who's Francesco Dagnino.
Oh, okay.
That us to look at that connection. So this is just for a bit of history. And then I was actually hoping to see how you deal with identity types. So can you give us maybe an idea of what's the intricacy there?
I can only say that it's terribly complicated. Nusha, would you be interested in commenting on the difficulty of identity types?
Okay. Hello, Jacopo.
Hi.
I do think that it's not complicated in the sense that you need to do invent more stuff other than what was just shown, but you just do the usual, you just do the usual stuff. But then the problem is that for example, things like subtyping, remember the functoriality, like the subtyping stuff has to be functorial, for example, with ID and composition. And Benedikt said that you can't just plug in ID. If you give it ID, it gives you ID. You need to have all these isomorphisms here and then to make all of these stuff actually type check. It's just that these isomorphisms are a bit annoying to work with and to write, and then the rules get big.
I see. You mean to write down in the syntax?
Yes. So if you look just at the rules in the paper, then you see for ID it's big, because all these isomorphism terms, you just want to write them, it's just big and too much work.
So I have a follow-up question, if I may. You axiomatize this language for CCTT using, let's say, axiomatizing the fibers of the fibration instead of the total category of the fibration. And I was wondering if maybe with the axiomatizing instead the total category, if that makes sense in some way. I don't know actually, but maybe doing that instead of the fiber-wise approach would make this coherence isomorphism disappear. Have you thought about this?
Who is answering? Benedikt, are you answering?
It would be great if you could answer.
Will it go away? Like, won't it appear in another way?
Well, usually that's the difference between indexed categories and fibered categories, in that the latter you have, you don't have coherence isomorphism hanging around. So that's.
I don't know how to answer, Benedikt.
Well, I also I think it's a good intuition. I mean, this is also why people avoid dependent types sometimes, because there you all have a similar phenomenon. Because when you have type dependency, then you have to use transports to put things into the correct type. I imagine that a similar phenomenon could appear here, where you just work with the total category or the total type, and then so it's possible, but I think in order to be confident, we would have to try it out. I think it's a good suggestion to try it out. But on the other hand, working fiber-wise is very. Okay, I will contradict myself here a little bit. Because on the one hand, we do want to be inspired by categorical considerations, of course. But on the other hand, we also want our syntax to be like a syntax. And from a syntactical point of view, it makes more sense to work fiber-wide, I think.
Of course, yes.
But yeah, so I'm torn between these two ideas. And which one should take precedence?
Okay, thanks.
Hello, can I ask a question? Thank you for the talk. Have you considered comparing this CCTT with just Martin-Löf type theory with ordinary function types? I was just thinking of like interpreting the subtyping as having an element of a function type.
Yusha, you're nodding. Do you want to answer?
Yeah, so can you go to the slide of sigma?
Here, somewhere?
Next one. The next, okay. So like the things that are like the composition that is in point 2, which we actually say, we kind of say that, say it to be the comprehension of the witness. These are like really like function types. So if you add to Martin-Löf type theory just non-dependent functions, they will be morphisms in the category C, which are like this. And by like this, I mean there is this commuting triangle of if you project on the left-hand side back to gamma and on the right-hand side also back to gamma, then it commutes. Like then they will be morphisms like this. So yes, I guess essentially what we are having extra is compared to this is that we are also having all these judgments regarding the type morphisms that then won't appear. But like for example, with the rule that is in, the rule that is in point 1, you can also say whenever you have such a function like number 2, then you also have this rule number 1. Then I don't know what the difference would be. It's not clear for me.
So maybe just a follow-up question. I was thinking of having something like interpretation between the two type theories.
Wait, I do not understand your question. But actually, can I add something to my previous response and then ask your second question? So can you consider that all non-dependent functions are just like all coercions and non-dependent functions are just nothing different, or is it just the same for you? Or
Sorry, I
so like
didn't.
when you have coercions that are like coercions as in like not explicitly coercing all the terms, right? Is this just the same as having non-dependent functions, or
So that was my original question, whether
yeah, so I mean, if you just think of them as they're just non-dependent functions and you don't have this judgment thing also that you have in rule 1, then I think it would be the same. But also now, can you repeat your second question, please?
I think this kind of answers the second question. Thank you.
Oh no, my answer was so bad that you don't want to ask questions anymore. Okay. Oh no. Benedikt, maybe you should answer now. People don't want to ask questions.
So, by interpreting, you mean maybe translating from one syntax into the other?
Yeah, that's what I meant.
Yeah. I think one could do that, interpreting translating the coercions simply into functions. I'm not sure where I want to go with the slides. That would be, I think that would be interesting. I mean, coercions are right as they are right now. I think they behave exactly like functions. And then there are two ways of making these coercions actually useful in some sense. On the one hand, one could try to, in a practical syntax, one could try to not write down these coercions so that they are inferred automatically. And probably that would mean that there should be at most one coercion between any two given types, because otherwise it sounds very dangerous. And that's exactly something that is studied in, if I go to the related work here, I think that's something that is studied in this work here, where there are translations between these different syntaxes. And in particular, so in this MLTT coerce, that is restricted to one coercion, at most one coercion between any two types. So in some sense, the category of types is thin. And there one could imagine, so maybe this paper is a bit what you're looking for, where there's a translation between different type theories, and maybe the answer to your question specifically is given indeed by the translation from MLTT coerce into something into this first variant MLTT with that does not have explicit coercions or something. Yeah.
Thank you.
So yeah. And then, as I said, another thing that one could do with coercions is what I alluded to here in this future work, that these coercions could somehow have a different behavior from other types. From other terms. That would, but then you cannot easily translate anymore.
Yeah, I had kind of a related comment / question, which is that I think I know you're inheriting the terminology of this subtyping from the Coraglia work, I believe, but I think traditionally coercive subtyping, normally people did imagine that there's at most one coercion between any pair of types. Just like prior to, a couple years ago, that was like how the terminology was used. And I'm a little bit like unsure of like, should I really think of this as subtyping or not?
Yeah.
Right. I just wasn't sure if you had any comment on that. This is just a terminological thing, not about the actual work.
No, I agree. I think in this work, we really focused on doing everything in great generality, and then with the idea in mind that to use it, one would really want to restrict, like to make it better behaved. In particular, one would consider a split syntax. One would probably have just at most one coercion between any two types, and so on. But just like the idea that comprehension categories are kind of a useful framework to study other things within that framework, we would hope that the CCTT is maybe a framework within which one can then look for suitable refinements or restrictions to actually do something useful. I mean, I think nobody would be interested in implementing CCTT as it is as a language, but it's more meant as a framework or so.
Sure. Yeah. I mean, I think what you're doing is well motivated by the semantics. It's just a
exactly.
question of like, is this actually subtyping, or is this just let me replace that word by some random word,
Right. Yeah. 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 A different word could be good. If you have a suggestion, let me know.
I do not.
Okay.
Yeah. Okay, any final questions? Okay, well, let's just thank Benedikt and Nayusha again. And we'll see you in 2 weeks. We have Bastian Knossen.
Thank you very much.